All right. Welcome everyone to the second lesson of Calc 1 for Technology. Today we're going to be discussing section 2.2, which talks about something called limits. So before we kind of define what a limit is, let's run through examples to kind of wrap our head around what's being said, what the idea is here, what's going on. So let's ponder for a bit and look at a function we looked at before in the last class, y equals 1 over x. Now, whenever we're talking about y equals 1 over x, right, remember that this has a specific domain and a specific range, as all functions do, right? This is a function, we call this f of x if we want to, just like that. And in this case, right, we have that the domain of this function is going to be from negative infinity to 0 and 0 to infinity, right? Because we can't plug in 0, we can plug in anything else we want to. Okay, now the range of our function is going to be the same exact thing, actually, because we can get any value we want except for 0, right? There's absolutely nothing that we can plug in that'll give us 0. However, there does seem to be a point that as we progress further and further and further, we might be able to say that as we approach something, we can get 0. So let's look at that, right? So what I mean is, let us take a look at the graph, okay, of y equals 1 over x. Notice that as I move in this domain, as I take my domain and I go all the way to the right, so I start here and we're going to walk and keep moving this direction, right? What's happening as I hit 10? Well, I get 1 over 10. 100, we get 1 over 100. 1,000, we're going to get 1 over 1,000, etc., 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 right? These numbers keep getting smaller and smaller and smaller until we get to a point where we're at 1 over a number like this. And it doesn't even have to be 10 something, but just imagine 1 over an incredibly huge number, right? What's that doing? Well, I mean, if I decided to take this value here and add it to the number 1, it's not really going to do anything. It's very going to be extremely insignificant. So because of that, as we move towards the right, so moving towards positive infinity, we can say that we can call this thing 0. So I'm going to write here as x approaches infinity, 1 over x approaches 0. So maybe something like this. So we say as x goes all the way towards positive infinity, 1 over x is going to go towards 0. We would say it's going to eventually kind of look like 0, even if it never equals 0 based on our range. Awesome. Okay, and of course that also applies the other direction, right? Because we're going to get, I would get 1 over negative 10 billion. And that's going to say that I have a really, really small negative number, which also approaches 0. So this goes both ways, really. So hopefully that kind of makes sense. So this is kind of what we want to start thinking of, that even if we can't reach a value specifically, that we say as we go a direction or as we approach something, that we can kind of squeeze it out. Okay, another example that we're going to do is we'll look at the graph of y equals x squared over x plus 4. Or I'll call this g of x maybe in this case. So what's going on with this function? Well, let's take this function and study what happens at a random value. We'll say 4. Okay, so we're going to look at what happens as x approaches 4. Okay, so as before, right, on the last problem, we kind of just kept plugging in bigger numbers to see what would happen. In this case, since we're approaching a specific number, we may want to look at more of what's happening around that number to know what's happening, right? So I could, plug in values. So I could do g of 3, maybe g of 5, maybe get closer, g of 3.5, g of 4.5, get a little closer, g of 3.1, g of, sorry, this one's going the wrong way. We want, 3.5. I just did the wrong way here. 3.9, g of 4.1, right? And you can continue to get smaller and smaller until we can kind of see what g of 4 looks like. And when you do that, right, as we kind of use a calculator, plug in, see what happens, right? You're going to get that this looks like it's going to approach 2. Now, this seems silly. Why do all that work? Why keep testing values, right? I mean, in the last case, maybe, but in this case, right? I mean, it's 4, right? It's not just some infinite, right? It's just a number, right? Look, we can just put it in. 4, g of 4 is going to be 4 squared over 4 plus 4. Well, 4 squared is 16, and 4 plus 4 is 8, and 16 divided by 8 is 2. I don't see an issue with plugging in 4. Well, there's not an issue in that case. In this case, as x approaches 4, g approaches 2. And in fact, g of 4 exactly equals 2. There's no concern there. So what's the big idea with this? What's going on? Well, that is going to make a little more sense as to why we want to do this once we look at the next example. Talk about our function h of x. So h of x is the function sine of x over x. Now, what's going on with this function? Well, let's see what happens if we let x approach 0. Okay, can I just put 0 into this? Let's see, sine of 0 is 0. X at 0 is 0. We have 0 divided by 0. That isn't anything, right? That's undefined. That doesn't have a value. However, if we plug in values like last time, so I could do maybe, g of -1, g of 1, g of -0.5, g of 0.5, g of -0.1, g of 0.1, right, etc. Keep making your values smaller and smaller and smaller. Eventually, kind of looking at g of 0, what we're going to get is, as we check those values, is that this actually looks like it approaches the number 1. And when we look at the graph, something interesting happens. While the value at 0 doesn't exist, there's actually, the graph actually goes towards the same place from both sides of this graph. It looks, basically, there's an open hole left in this graph, but everything else kind of follows suit. It does something similar all the way across, which is very interesting because, you wouldn't expect to get a value out of this, and we can't technically, but as we approach 0, our graph has a specific behavior. It says as x approaches 0, the graph shows us that g of x approaches 1, which is very cool. It's almost like we can't, right? It's basically showing that the graph, the function still has a specific behavior around a point, even if the function doesn't necessarily exist at that point, right? And it's going to be interesting for us. It's going to be good for us to want to study the behavior of those sorts of things, which is where we take this and we get this concept of limits. So let's run through some quick talk about what a limit is. So a limit says basically as x approaches a, then the limit tells us what the function does. Right? So it says, it kind of tells us what the behavior of the object is, right? Or what the function is at that point, right? So the way we write this, the kind of notation for this is we'd say the lim as x approaches a of f of x, right? Now, it's not true that this always is going to be a value, right? We saw in the last few examples, right, that the limits that we did always had a specific value attached to them, right? But the issue is that that's not always the case, right? So maybe a real easy example, right? Let's look at the function f of x. And we'll do -1 when x is less than 0 and 1 when x is greater than 0. So you remember this is a piecewise function like from last time, okay? So we don't have a value divided to 0, right? Now, so our graph looks something like this, right? Because if I have a constant function, that's just going to be a straight line. If I just have a number, then it's just going to be the number all the way through. Okay, so what's happening in this case? As I look on the left side of this graph, right? What's it doing? What's it approaching? Well, it's approaching -1, right? All these values are going to give you -1. But on the right side, it's approaching 1, right? So they're not approaching the same thing. So the limit as x approaches, in this case, 0 of my function, I would say does not exist, right? However, what if I have, we'll say, I could get the function right in there, but we'll say f of x is instead this time, we'll say that it's x squared when x is not equal to 0, but we'll say it's 4 when x is equal to 0. Okay, so what does this go look like now? Well, on the left side, we're going to have parabola. All right, so we're going to have parabola, but right at that point, we get the number. So our graph is going to look something like this, right? Now, what about the limit in this case? Well, the limit as we approach 0 of this function, right? We don't care about what happens at the point, remember. We care about what's happening as we approach that point, right? Because sometimes the value doesn't even exist, right? The value does exist in this case, right? But the value does exist in this case, but in this instant, the limit doesn't actually go to the same place, but the limit still exists, right? Let's look. So as we approach 0 from the left side, it's going down, down, down. It's going towards the 0 point. And from the right side, it's going towards the same place. So the limit as x approaches 0 of f of x is actually 0 in this case, because as we're approaching 0, our graph behaves like x squared, right? So we just do 0 squared, which is 0. Okay, so here's an example where the limit kind of does exist. Okay, so that's why I say as x approaches a, then the limit tells us what the function does, right? So the limit essentially, you know, if we want a formal definition of the limit, the behavior of a function as its input, I'll say moves towards a given value. So this might be a good definition of a limit to go off of for us. It's basically the behavior of a function as its input moves towards a given value. Okay? As it's not the behavior of the function at that given value, it's as it moves towards that given value. Okay? So there's a little bit of a difference here, right? Although we can't plug it in, we can still study the behavior as we approach that point. Okay? So now let's go back real quick and talk about we'll pull up the f of x is -1, one example again, right? Can we say, I mean, we still, maybe from the left and right, still have an idea of what the value is approaching, right? Exactly. We still have an idea of what's happening to the graph, right? So from the left side here, I get, right, as we saw, the limit would approach -1 from this side and would approach +1 from this side. So the limit at 0, maybe as we're approaching 0 from both sides, doesn't exist, right? But we can actually use this example to also talk about one-sided limits. So we were just, the concept we were just looking at was both-sided, right? Coming from both sides to the same place. But we can also have a one-sided limit, right? So give me 1 second. That might make the lighting a little bit better on there. Okay. Let's do one more thing. Hopefully that'll make the lighting a little bit better to see the board. Most of the stuff I was saying before, aside from, which you should be able to see the definition still, I want to write down, but we want to be able to see a little better with this. So anyway, continuing on with the lesson, let's talk about this idea of one-sided limits. So a one-sided limit, right, sounds exactly what it sounds like. We only care about what's happening from one side, right? And these are actually important. We don't just care what's happening from both sides, although that'll come in handy in some cases, right? We only care about coming from one side or the other, right? So in this example, right? So a one-sided limit is just saying the limit as x approaches a from the right, or maybe the left side. So whenever we want to mark we're coming from the right side, it might be a little hard to see, but I'm using a plus, okay? So I'm gonna write, let me write that a bit bigger. I'm going to say the limit as x approaches a from the right side in that case. So I would use a plus to do that, right? Versus I'm coming from the left side, I'll use a minus, okay? And so what that means is that I'm only going to look at the behavior of the function as approaches from the right side or the left side. In this case, it'd be the left side, but if this was a plus, then it would be the right side, right? So looking at this function, what is the limit as x approaches 0 from the right side? What would we say? Well, from the right side, this is the right side of 0. So we approach it, our value looks like 1. So we would say 1, right? And we don't have to worry about the other side in that case. So in that case, the limit does exist, right? And if we decide to change it and look at the left instead, well, I would look at the left side and my graph is going towards -1. So therefore, that would be, I would call that the value at that point, okay? So even if a limit at a point doesn't necessarily exist, we could still find a left and right hand side limit, okay? And that actually leads us to an important result, which I'd like to write, which says that this is a theorem, or you can say a definition. It's really more of a theorem but it doesn't matter too much for this class. The limit of a function exists if and only if. So whenever I say if and only if, it means that this applies both ways. So the first thing implies the second thing, and the second thing implies the third thing. Basically, they both have to be true. If one's true, then the other definitely is. Okay, the limit of a function exists if and only if both of its one-sided limits exist and equal the same thing. I.e., the limit as x approaches a, right? So i.e., this basically means that the limit as x approaches a of f of x exists, means that the limit as x approaches a from the right of f of x equals the limit as x approaches a from the left of f of x. Okay, so right, so what we're saying here is that hopefully you can see that well enough. I can write that a little bigger if I need to. I'll probably do that. So once again, if the limit as x approaches a of f of x exists, implies that, or it's the same thing going back and forth, that the limit as x approaches a from the right side of f of x equals the limit as x approaches a from the left of f of x. That they both exist and they equal the same exact thing. Okay, so hopefully that makes sense. That's how we define if a function, if the limit of a function exists or not. And so that will be maybe useful for us moving forward. Now, is it possible that there's a case where only one of the one-sided limits exist? Or is there a case where neither of them do? Well, yes. I'll show you an example where only one exists. We don't need to worry about a case where both of them don't exist. Because most of the time it would probably boil down to pretty silly examples, but examples nonetheless. So let's think about the function, the square root of x minus 2, okay? What is the limit of this thing as x approaches 2 from the left side? I'll give you a moment to think about it, right? So we're saying 2 from the left side. That means we want numbers that are less than 2, right? Smaller than 2, from the left side of 2. So if I pull a number, let's say 1.9, that's from the left side of 2, and I plug it in here, is that okay? Well, no, that doesn't work, right? Because those are going to give me negative numbers inside of my radical, which means that the number is imaginary, right? Which in this class, we're only concerned with real numbers. So this limit does not exist. However, what about the limit as x approaches 2 for the right side? Well, now we're plugging in numbers that are bigger than 2, right? That are to the right of 2, right? So we're going to put those in, and as we move closer and closer to 2, we're going to see that this is going to turn into 0. And in fact, right, if we just put 2 in there, which we could, it would just give us 0. So that works, right? But the left-hand side doesn't work because we can't put a left-hand number in there and get a real number out of it, right? Only the right side works like that, okay? So in this case, the limit does not exist, but in this case it did. And so therefore, we can say that limit exists, okay? So some important examples to keep track of, I think maybe the end of the homework is examples like that. So want to keep that in mind. Okay, great. So let's move on to some examples. Example problems. Everybody loves those, right? So let's do some example problems. Okay. Example problem number one, right? Because now we don't have calculators. You can't just keep plugging in values endlessly. What sort of problems can we do on an exam or a test, or or a quiz, of course? Well, let's take a look at the problem. The limit as x approaches 3, just 3, not right or left, of x squared minus 9 over x minus 3. Okay, so could I put 3 into this? Well, let's see. If I put 3 up here, I get 3 squared. 3 squared minus 9 is 0. Okay, and 3 minus 3 is 0. Okay, that's not going to work, right? Because we're dividing by 0 in that case. So we can't just plug in 3. However, let's take a look at that top part. Does that look familiar? Right? It's x squared minus 9. Does that look familiar at all? Well, it should, because that's a difference of squares, right? What is 9? It's 3 squared, right? We have x squared minus 3 squared. This is the difference of squares. And whenever I have a difference of squares, I can factor that. So I can factor this. So I'm going to get the limit as x approaches 3 of x plus 3 times x minus 3 over x minus 3. Okay. Right? Now what's going to happen, right? Notice we have x minus 3 over x minus 3, right? And again, the limit is as we approach 3, we're not at 3. And because of that, these are not 0 here, so I can easily just divide these two numbers, and that's okay. So that leaves us with the limit as x approaches 3 of x plus 3. Well, what now? Is there a problem with me plugging in 3 now? No, absolutely not. Right? I keep moving that 3 in the same place. There's no problem with that. I can easily just plug in 3. So when I do that, I get 3 plus 3, which is 6, which is exactly the limit of the function. Okay. Now, why did that work? Why could I just replace this function with this one, right? Even though there's a slight difference, because this one I can't put in 3, but this one I could. Why was that okay? Well, let's think about this, right? So we'll draw the graph of the function, which it's the graph here is just x plus 3, right? It's just a line. So it's got a y-intercept of 3 and a slope of 1. So it's going to look something like this. Good. And our point of interest here, right, is we want to know what happens when we approach 3. So let's kind of mark that on our picture. Right there, that big dot. Okay. So this is x plus 3 right here, right? What is the difference between this graph and this one? That. If you can see it, I just took that big dot, the big black dot in the man on the line, and made it an open dot instead, right? These two things are the exact same graph, except this graph is missing that point. It's missing the 0.36, unlike this line. Okay? So, because of that, the behavior of the graphs as they approach that point are doing the exact same thing, right? So I can just use this graph because it's going to exhibit the same exact behavior as this one is as we approach the number 3. Not at 3, but as we approach 3, right? And in this case, right, this was a lot easier. We could actually plug into this one and get 6, okay? So this is kind of like a representative function of sorts in place of this one to help us understand what the limit is, okay? So you might see a couple of examples on the homework like that that say what is that representative function, and that's what we're talking about in that case. Okay, so there's our first example, okay? So try to see if you can whittle this thing down, right? Especially as we're approaching a value to a more simple function, and then be able to plug in from there. Okay. Example number 2. Example number two. Okay. What about example number 2? So let's do the limit as x approaches 2, why not, of x squared minus 5x plus 6 over x squared minus 3x plus 2. Oh, well, we've got a couple of polynomials now, one on the top and one on the bottom. So this is a little interesting. Let's see, can I put 2 in? Well, we get 4 minus 10 plus 6, that's 0. Okay, and put 2 in down here, we get 4 minus 6 plus 2, that's also 0. So this is actually 0 over 0 still. I think we might be able to factor this though. So let's investigate that, right? Let's see. So I'm going to take the limit as x approaches 2, and I think that we might be able to take the top and bottom and factor it. Right, so we can kind of, because right, last time we canceled out that x minus 3 term. So let's try to cancel out an x minus maybe another term, right? It'd probably be x minus 2 potentially, we'll see. So we want 2 numbers that multiply to give us 6, but add up to get minus 5. Well, that's going to mean that both numbers, so if 6 is positive, right, both numbers have to be the same sign, but 5 is negative, so that means they both have to be negative numbers. So we're going to have minus and minus, okay? So let's think what 2 numbers multiply to give us 6. 1 and 6. 1 plus 6 is 7, that doesn't work. 2 and 3. 2 and 3 gives us 5. So we're going to get x minus 2 and x. Good. Okay. Down here, we have the same story, right? 2 is a positive number, but 3 is negative, so both of these have to be minuses. Now, what 2 numbers multiply to give us 2? Well, we really only have a select option there. It would just have to be 1 and 2. So, we'll put 2 and 1. Okay. And you can check that, of course. Negative 2x minus x gives us minus 3x. Minus 2 times minus 1 is positive 2. So we're left with this, right? Now what's going to happen here, right? We see that x minus 2 and x minus 2, now they can cancel. So we're left with the limit as x approaches 2 of x minus 3 over x minus 1. Okay? Which now I can just safely plug 2 into, right? So what happens when I put 2 into that? I'm going to get 2 minus 3 over 2 minus 1, which is negative 1 over 1, which is simply minus 1. And so that would be our final answer. Okay, that's all you have to write, right? If it just asks for a limit, then all you have to write in that case is minus 1. Okay, does that make sense? Hopefully. Awesome. Okay. Let's move on to example 3. I'll try to come up with a harder one for you guys. Let's see, let's do the limit as x approaches 1 of x squared plus 3 over x plus 1. Okay, I gotta factor this, right? So let's factor it. Let's see how we're gonna factor this. Let's take x squared plus 3 and let's wait. Can I wait? Wait a second. Let's not jump the gun here real fast. Let's notice we have x squared plus 3. I can plug 1 into that, of course, that's fine. And x plus 1, I can also just plug 1 into that. I don't need to try to factor this, right? I can just plug in, right? I can just take 1 and put it in. I would get 1 squared plus 3 over 1 plus 1, which is 4 over 2, which is 2. Oh, well, that wasn't that hard. Right? Always, always, always check and see if you can plug in the number first. Okay? That's what we want to try to do each time. Don't just try to factor it every time, because sometimes you might not be able to factor it. Sometimes it's a lot easier than you think. That's going to save you a lot of time in these sorts of situations. Okay? So there's example number 3. Example number 4. Okay. Now, so those are a few examples of limits that are at a specific number, right? Where we can really factor nicely and we can kind of work with things to make something work. Now, let's talk about a different case. What happens if we're approaching infinity? What do? Let's get an example problem out, right? So we're gonna have the limit as x approaches infinity of x squared minus 4x plus 5 over 2x squared plus 3. Okay. So let's see. I could try to plug in infinity, I guess, but that's not really going to get us too far. Get infinity over infinity. That's, I don't know what that is. It's not infinity. We can't just say it's infinity. Okay. And I don't really know if I can factor these, but in this case, we don't typically want to try to factor because it doesn't really help us out much anyway. So what could we do? Well, maybe let's try to attach ourselves to something that we're familiar with, right? That we're more familiar with how to handle, right? Let's go back to the very first example we talked about here, right? We said we took the graph y equals 1 over x, right? And we looked at it and we said, okay, right, clearly as x approaches infinity, right, 1 over x is going to approach 0, right? It's going to keep getting smaller and smaller and smaller and smaller until there's basically nothing happening, right? So we can call that 0, okay? So a fact that we have, right, which I'll write up here, a fact is that the limit as x approaches infinity of 1 over x to x is 0, right? And this actually is true for any like normal power, right? 1, 2, 3, 4, 5, 6, which is the normal case we'll experience, right? I'll just write x to the n power. This is true for any of those, right? If it's x squared, it'll just decrease faster. X cubed faster, x to the 50th, right? Clearly a lot faster, right? So that's always 0 for all of those, right? So if somehow we can kind of take this problem and make it look like this one in some way, then this is going to help us out a lot. Okay, so first, it doesn't look like I really have any 1 over x to a power, right? So maybe we want to try to force that in here first. How could we do that? Well, let's take, make sure this is a 5. There we go. Let's take the top and bottom and maybe try to do something to it, right? Maybe multiply or divide something from it so that we can make everything look either like this or maybe just a number, right? Because the numbers are easy to work with, right? What is the limit as x approaches a of a number c? Well, there's no x here, right? There's nothing that happens, right? So clearly this is just going to be c, right? And this applies if it's a number, if it's infinity, it doesn't matter. It works the same way. Okay? So if I can just get a number, or I could get 1 over x to a 1, 2, that would be helpful. So how could I do that? Well, the highest power here is x squared, right? In either case. And if we divided by, if we got rid of that x squared, right, that would give us numbers and we could, everything else is a smaller degree. And so that would give us 1 over something. So let's take the top and bottom and divide by x squared or multiply by 1 over x squared. It's your preference how you choose to see that. And when we do that, I'm going to get the limit as x approaches infinity of 1 minus 4 over x plus 5 over x squared divided by 2 plus 3 over x squared, right? If you weren't following necessarily, let me kind of run through this again, right? So x squared divided by x squared gives us 1. 4x divided by x squared is 4 over x, right? Because you divide by 2 by x, 2 x's, right? So you have 1x left on the bottom. So we get minus 4 over x. 5 divided by x squared is 5 over x squared. That's pretty simple. 2x squared divided by x squared just gives us 2. And 3 over x squared, or 3 over x squared is simply just 3 over x squared. Okay, so this is what we're left with here, right? Now, we're still at a bit of an impasse because it still doesn't quite look like this. There's pieces inside it that look like that, but not necessarily, it doesn't, like, I'm still kind of sketchy maybe of plugging it in there as it is, okay? So the way we're going to figure that out is I need to use a few limit laws, okay? Which I won't ever ask you to kind of write them out on the test, which ones you're using, but we need to intuitively know that they work, that there's a reason that we can do the thing that we're doing, okay? So let's do that. I'm gonna take, let's see, so I'm gonna write limit laws here. So assume, so I'm gonna write here just to assume that the limit as x approaches a of f of x and that the limit as x approaches a of g of x exist. Okay, so both of those limits, so just we have an f and a g, we're going to assume that both of those limits exist. Okay, from here, I'm going to get a few results. The first result, so we're going to have 5 different results. Let me write all of them. I'll leave a bit more space for the fourth result. Okay, hopefully you can see all those. Cool. Okay, result number 1. Give me 1 moment. Hopefully that might make things a little bit better. I'll go and continue writing from here. So if I have the limit as x approaches a of f of x plus g of x, then this is the same thing as the limit as x approaches a of f of x plus the limit as x approaches a of g of x. Okay, so hopefully you can kind of see what's happening here. Essentially, I'm saying the limit as x approaches a of f of x plus g of x together inside one parenthesis is the same thing as the limit as x approaches a of f of x plus the limit as x approaches a of g of x. Okay, and the next one's going to follow suit. It's going to be the same exact thing, and I might actually make a bit more room for these. 2, 3, 4, 5. Okay. And so we're going to say for number 2 that the limit as x approaches a of f of x minus g of x is equal to the limit as x approaches a of f of x minus the limit as x approaches a of g of x. Okay, so notice that that limit kind of phases through the parentheses here and goes to each individual term. So we're going to have the limit as x approaches a of f of x minus the limit as x approaches a of g of x. And just as with plus and minus, this actually also works for multiplication, which is the next one. So we're taking the limit as x approaches a of f of x times g of x and this is the same thing as the limit as x approaches a of f of x times the limit as x approaches a of g of x. Just like that. Okay. So with that all being in mind, with that being said, right? What about division? Well, division is also allowed under certain conditions. And let me clarify that. So we need, let g of x not be equal to 0. So we don't want g of x to be 0, right? And of course, right, because if it's 0, then that would be a problem. And the limit as x approaches a of g of x to not equal 0. So whatever g of x is, we also don't want its limit to be 0 either. Okay? So g can't be 0 itself, and the limit can't be 0 either. And the reason for that, right, is because if I'm going to write the limit as x approaches a of f of x divided by g of x, then that is the limit as x approaches a of f of x divided by the limit as x approaches a of g of x. Okay, so do you see what's going on there? In essence, that if these two things are dividing, then I can just take the limit to the thing on the top and bottom, right? As long as those conditions are satisfied, where g is not equal to 0 and the limit as x approaches a of g of x is not equal to 0. Okay, since there's a little bit of glare, I might, let's see. I'm gonna kind of box this in real quick. Unfortunately, actually, let me just use this little corner over here. I'll sit down for this. So for number 5, right, so I'll move that to this corner. So maybe we'll make some room for the final solution. Okay, so number 5 is that if I have the limit as x approaches a, and this is a pretty simple one, right? If I have a constant times f of x, a number just times f of x, any number, right, c times f of x, then that means that constant is going to come out in front times the limit as x approaches a of f of x. Cool. Pretty simple, nothing too crazy. We just kind of bring that constant out. Okay, so these are all the laws that we want to use in order to be able to evaluate, problems like these. Okay, so as we go through, I'm going to be listing which ones I'm using at each step. But of course, I don't expect you to have to do that. But I want you to know these in some regard. Okay, so we have our equal sign here, our next equal sign, so number 4, right? Because I'm dividing, right? So I want to be able to split up the top and bottom, right? I want to do the limit to the top and the limit of the bottom. So I'm going to get the limit as x approaches infinity of 1 minus 4 over x plus 5 over x squared divided by the limit as x approaches infinity of 2 plus 3 over x squared. Okay. Now, I'm going to use a few of them at once, right? Because I want to separate the division one, of course, right? But I am going to use numbers 1 and 2, but that's really easy to kind of see, right? We just kind of phase through the addition and subtraction. But I'm also going to use number 5, where I take that constant, right, in each case and bring it out, right? So I'm taking that limit and I'm moving it to each piece, but also whatever number is with the 1 over x squared, I'm going to kind of pull those out, right? Because I want to be able to use our fact, okay? And of course, once you kind of see how this works, we could put any number here, but for the sake of completeness, I'm going to use all these here. So I'm going to get the limit as x approaches infinity of the number 1 minus 4 times, so again, that's 5 coming in, where I take the 4 that was here and kind of bring it out in front. And that's going to be times the limit as x approaches infinity of 1 over x plus 5 times the limit as x approaches infinity of 1 over x squared divided by the limit as x approaches infinity 2 plus 3 times the limit as x approaches infinity of 1 over x squared. Okay. Cool. So now what happens, right? The limit as x approaches infinity of 1 is 1, right? We talked about that earlier. If it's just the constant, then the limit is just the constant, okay? The limit as x approaches infinity of 1 over x, well, that's just 0, right? So this whole thing is just 0. So 4 times 0 is still 0. 1 over x squared, which was a little harder to see, but hopefully you can kind of pull it out still. That'll be 0. 5 times 0 is 0. 2, we just get 2. And 3 times 1 over x squared, which again is going to be 0, right? So this guy is, and this limit is 0, this limit is 0, and this limit is 0. And of course, a number times 0 is still 0. So we're going to be left with 1 minus 0 plus 0 over 2 plus 0, which is just going to be the number 1/2. Okay, that's all it is. So really not too bad. I did a lot of explaining on this one, but it's just because it needed a lot of explaining to get it to work out, right? In essence, this really isn't too difficult a problem once you see it, especially when you notice, for those who have keen eyes, that at the beginning of the problem, we could see the limit, couldn't we? Right? What's the coefficient on the top x squared? It's just the number 1. What's the coefficient on the bottom x squared? Well, it's just the number 2. 1 over 2. How about that? Right? Because what's going to happen as we go towards infinity is that this 4x, this 5, and this 3 aren't going to matter. It's only going to be the x squared terms. And so as we go towards x squared, or as we move towards infinity, that's kind of all we're seeing. And so you're just going to be left with 1 over 2. That's really all it's going to be left. I do want you to still work it out like this, but that might be a good check just to know that you're doing things right? So you don't get things mixed around. It should, if your degrees are the same, so x squared and x squared, right, or x cubed, x and x, then your limit is going to be just the ratio of the two coefficients, which in this case is just 1 over 2. Okay. We got a few more examples here. Or sorry, not a few more, a couple more. Don't worry, I won't keep going for too long. So examples again. Okay, number 5. So I said if they have the same degree. What happens if they have a different degree? More specifically, what happens if the degree of the top, so we're still approaching infinity, but what happens if the degree of the top is less than the degree of the bottom? Well, in this case, what we could do, right, is you can still apply the same exact approach, right? I can say, well, let's divide the top and bottom by one of the powers, right? Which I would encourage in this case, the easiest thing, as pointed out in the last class, is just to take whatever the highest power is and divide it, okay? So in this case, again, the highest power is x squared. So I'm going to divide the top and bottom by x squared, okay? So what happens when I do that? Well, I'm going to get the limit as x approaches infinity of 1 over x, right? Because x over x squared, you have 1x divided by 2x's, that leaves you with 1x on the bottom, over x squared divided by x squared gives us 1, plus 1 divided by x squared, 1 over x x squared. Okay. Now, what about this? Well, what's the limit as x approaches infinity of, right? And remember our limit laws, we can apply it to the top and bottom and go through each thing, right? So each piece that's being added or subtracted, right? Whether on the top or the bottom, I can take that limit to. So what is the limit as x approaches infinity of 1 over x? Well, that's 0. What is the limit as x approaches infinity of 1? It's just 1. What's the limit as x approaches infinity of 1 over x squared? Again, using our fact, right? And that was, so use the same fact for that. The limit as x approaches infinity of 1 over x to the n power is 0. 1 over x squared, the limit of that is 0. So we get 0 over 1 plus 0, which is, okay? Which leads to another interesting result, which is if the degree of the top is smaller than the degree of the bottom, then the limit should be 0. Now, again, I encourage you to check it, but the limit's going to be 0. Now, I would encourage you, you can also just divide by x, divide by the power of the top to be able to solve this problem. And that would also work. There's nothing wrong with that. Just make sure to know how you're applying your limit laws and how those work. Okay, but you'll get the same answer. You should get the same thing. So either way, it's fine. Okay. Last problem. Number 6. We're going to take the limit as x approaches infinity of the square root. Oh, didn't expect to see that one, huh? Thought we were just doing all these rational functions. Now we got a square root thrown in. Geez, what are we going to do? We're going to take the limit as x approaches infinity of x squared minus, actually, well, I'll do x squared plus 8. And then minus x. Well, at first glance, this doesn't seem like much of a problem. It seems like we could probably figure it out. I mean, it's not like we're dividing anything to make anything weird. What's going to happen, right? We're just going to get, if I put infinity in, even though it's not really a number, but I'm going to get infinity squared plus 8, right? That's just infinity. Square root of infinity is infinity minus infinity. Okay, well, maybe if I just subtract 2 infinities, right? I just get infinity. However, that's not necessarily the case. As those infinities, depending, could be the same size, they could be, we don't know. And so it's hard to tell with an example like this, especially because now, let me give the benefit of the doubt that if I didn't have a square root on this problem, and you put infinity in here, this would be x squared to an infinity versus minus x as infinity. Which one's bigger? The x squared, right? So if I have infinity squared minus infinity, right, assuming they're the same size, in that case, you're plugging in, this one would clearly win. And so we would say in this case that this limit's infinity. But that's not the problem we're dealing with. That is not the problem we're doing. The problem we're dealing with is the square root. What is the square root of x squared? It's x. So these are very much the same size. We could find out that 8 doesn't really do anything. So we're going to need to do a little bit more work on this. So that x squared really is an issue. If only I could get rid of that or move it somehow, then that would be useful. Okay, so right, we need some way to be able to just move it, do something with it, right? And many might think that the first idea could be to square, right? Well, what if we just square both terms? Well, you can't just do that without doing it to the bottom, but also remember, that if I take an a plus b and I square it, this is not the same thing as a squared plus b squared, okay? Because we have to FOIL this out, right? This is the same thing as a plus b times a plus b, which when we FOIL, as we saw earlier with other factoring examples, we're going to have a squared plus ab plus ab inside plus b squared, which is going to give us a squared plus 2ab plus b squared, right? If we just tried to square that thing, we're still going to be left with this 2ab term, which means that I'm going to have 2 times x to the square root of x squared plus 8 times x, which just made things worse, actually, because even though these squares here take care of the square root, not so much in that middle term. So that's not necessarily what we want to do. So what could we do? Well, let's recall an example from earlier. Do you remember what we did in this problem? So we have the limit as x approaches 3 of x squared minus 9 over x minus 3. Well, we took the top and we split it up. We factored it, right? We factored it because it's a difference of squares. So this problem became the limit as x approaches 3 of x plus 3 times x minus 3 over x minus 3. Now, here's something interesting that happens, right? We have just these two things that are squared and there's no extra term, but we could still factor it into these two pieces, right? So, right, if I just want to square this term and I just want to square this term, then I ought to write it, maybe use some sort of difference of squares idea, right? So what that would require is not for me to multiply this by itself, but for me to multiply it by, right? We don't want to multiply by another x minus 3. We want to multiply by an x plus 3, right? Or in this case, we're going to multiply by x squared plus 8 plus x. Okay? Multiplying by what's called its conjugate, right? Where all that happens is I change the sign in the middle. Now, if this isn't made clear while we're doing this, again, remember, I can't just do multiply by the top. I have to do the top and the bottom. So I'm going to multiply, I'm going to put an x squared, square root of x squared plus 8 plus x in the bottom. So now what happens whenever I multiply that top out? I get the limit as x approaches infinity of x squared plus 8 times x squared plus 8 plus x times the square root of x squared plus 8 minus x times the square root of x squared plus 8. Those cancel each other out, don't they? And then we have x times x, which gives us minus x squared. Over the square root of x squared plus 8. So notice that got rid of that pesky square root on the top without ruining the problem. Okay, so now what's going to happen, right? We have x squared minus x squared on the top, which perfectly cancels out nicely. And then I get the limit as x approaches infinity of 8 over the square root of x squared plus 8 plus x. Right? Now, again, this is a little different than maybe what we're used to seeing, right? But let's consult this example again, right? So, right, we saw that everything's happening on the bottom. It just keeps getting bigger. And then there's 1, right? And so that limit went to 0 as I went towards infinity. Now look here, we have 8, and then we have the square root of x squared plus 8 plus x. As we go towards infinity, what's going to happen to this thing? It's going to get huge. It's going to blow up, right? So instead of having to work some sort of kind of weird dividing piece into this, all we need to do is just say, well, this is going to be 8, but this thing keeps getting bigger. So I could have 8 over 10 million, million, million. which is going to approach the number 0. Okay. Hopefully that makes sense. If it doesn't, just reach out to me and I'll try to explain as I can. I'm trying to stray away from methods that 165 would use in some of these problems, just because they're not as necessary in this class, but hopefully that makes sense in terms of the explanation, because this is all the reason that this was an issue is because it was minus. But this is plus now. That clearly is just always getting bigger. So you have 8 over infinity, another infinity essentially, which would be 0. Okay. Cool. So last just really quick topic I want to mention while I'm thinking about it is something called continuity. So what does it mean for a function to be continuous, right? You've probably heard that word thrown around before, continuous function, and you just kind of picture something that's it's nice. It just seems nice. And that's, I mean, really, I mean, a pretty good idea. It's what we call a nice function. It's a function that is connected, right, at every point. So this is an example of a continuous function, right? But this is not, clearly. There's so many breaks in that. It doesn't even, it really is strange. There's so much breaking in pieces that it gives us a lot of issues. Okay, so this one is a continuous over this piece of the graph at least, but this one is very continuous, okay? And whenever we're talking about something being continuous, this actually ties in a lot to limits. We actually can get a definition of continuity using limits, which says that f of x is continuous at x equals a if, I'll just say if, so this is true if this thing is true, okay? Even though it technically should be like an if and only if statement, but we will worry about that as before. So if the limit as x approaches a of f of x is equal to f of a. What does that mean? That means that I can just plug in the number and it works out nicely. Okay, so the limit as x approaches a of that function is that function itself. Okay, so let's look at a couple examples of this, right? Examples where they're not originally continuous, but maybe we could make them continuous. So first example I have is, let's take the f of x is the function x squared when x is not equal to 0 and 1 when x is equal to 0. Okay, so this is what we've seen earlier. I think I used 4, maybe I'll stick with 4. But the graph is going to look something like this. Probably we put a dot at 4. And the rest of the graph looks like that. Okay, so what is the limit, right? We established before the limit as x approaches 0 of f of x is 0. However, f of 0 itself is 4. So what does that tell us? That means the function is not continuous at that value. Okay, clearly, right? We could use that test to say, so we can use that to check it at any point, right? As long as the limit at that point is equal to the function value at that point, then the function is going to be continuous at that point, right? But in this case, they're not, right? Because the limit of our function goes to 0, but the function value itself we define as at 4. So how can we fix this? Well, let's get rid of this silly defining, right? How this x is not equal to 0 stuff here, and let's just call it, let's just right? F of x is x squared. Well, at 0, we're going to get 0 for x squared, right? So now the values are the same. So is that function continuous at 0 now? Absolutely. We kind of filled in the hole. So now it's all connected. So because the limit is x squared to 0 f of x equals f of 0, which is 0 in both cases, then that function is continuous. Okay, one more. We established earlier that the limit is x approaches 0 of sine of x over x equals 1, right? What was the issue with that function? If we remember, right? Well, it's that that sine of 0 over 0, we'll call this function h of x, I think we did before. H of 0 does not exist, right? So clearly they're not equal to each other because this value doesn't even exist. So what do we do with that? Right now this function is discontinuous at that point. How can I fix that? Well, let's redefine h of x. I'm going to say h of x is equal to sine of x over x when x is not equal to 0 and 1 when x is equal to 0. Now, what does that do for us? Well, the limit still of 0 sine of x over x is clearly still equal to 1, of h of x is still equal to 1, right? Because we're not at 0, whereas we're approaching 0. And on either side, we're approaching 1. But now we've defined the function in a way that we actually have a value at 0, which is 1. So now these are both equal and they both hit the same place. So that open hole has sort of been filled in a way, and now it's a continuous function. So now we have the case where the limit is x approaches a of f of x is equal to f of a. Just like that. Okay. Well, thank you all so much for watching this video on limits and a little bit of continuity here at the end. This is a topic that you'll kind of continue to feel the pulse of throughout this entire course. And so I would encourage you just to really think on it and definitely practice the exercises I provided. We don't get to cover it as much in this class as 165 does. As unfortunate as it is, I know. I know you guys wish you could more. But I'm glad we get to cover it at least a little bit because it'll help to explain the upcoming and everything else we're going to learn for this class. Anyway, thank you for watching again. I hope you'll have a wonderful day. Please get in contact or just message me if you have any questions.